My name is Dr. Samuel R. Hedman, and I'd like to share with you an exciting new discovery that I've recently made in physics. So, back in 1935, Einstein and others suggested that there might be more physics hiding underneath of quantum mechanics. Now, this is despite the fact that Einstein is actually one of the co-founders of quantum mechanics, and it's not that he thought quantum mechanics was wrong. It's that he thought it might be incomplete because there are things that it simply cannot explain. And this idea eventually became known as local hidden variable theory. Then, in 1964, this other guy named J.S. Bell came along, and he thought he had an ironclad way to disprove Einstein's idea of local hidden variable theories once and for all. And then, over the next several decades, people did all kinds of experiments to try to see who was right, Einstein or Bell. And the prevailing idea eventually became that Bell was correct and Einstein was wrong, and that local hidden variables were simply incompatible with quantum mechanics, which is what Bell set out to prove. And in fact, the 2022 Nobel Prizes were actually awarded to these experimenters for doing this work. However, it may be that they were not testing what they thought they were testing. And what I'm going to show you today is that it's actually possible to disprove Bell's idea. Now, this does not fly in the face of all those experimental results. What I'm also going to show you is that those results agree with Einstein's idea after all. So join me as I take you on this journey through these exciting new results. Hi everybody, welcome to our talk today. Local hidden variable theories agree with quantum mechanics after all. And it's based on the paper called Local Hidden Variable Models That Agree with Quantum Mechanics for All Systems by S.R. Hedman, which is myself. And you can find that on Zenodo, which is CERN's general posting site. So first, to understand this idea of hidden variables, we have to begin with the idea of completeness of a physical theory. So in 1935, Einstein, Podolsky, and Rosen, EPR, said that every element of the physical reality must have a counterpart in the physical theory. Very, very reasonable. So in other words, if we're trying to describe reality with some kind of mathematical model, our model should contain all the information in it that describes what happens in reality. Okay, so this is a good necessary condition for the completeness of a physical theory. Very, very reasonable. EPR said that quantum mechanics, which we'll call QM, may not be complete. And there are several reasons they gave, and I'm going to give you some modern, easier to understand reasons here. Example one here is that quantum mechanics allows states of superposition. So what we mean by that is a state can be up and down at the same time. This is very different than like a coin, which would be heads up or heads down. We talk here about a quantum coin would be heads up and heads down. And these numbers here are coefficients that describe the amount of upness and downness that they can be at the same time. Okay, so this is spin up and spin down simultaneously. That's the idea behind quantum superposition. But measurement collapses the superposition. It's almost like it bursts the bubble. Okay, so if we're going to measure this state, it will give us only up or down, and the probabilities for each one are given by the square magnitudes of these coefficients. And so this sort of is the heart of one of the major limitations of quantum mechanics, is that it can only tell us the probabilities. It can't actually tell us when we will get each one of these particular outcomes when we measure it. Okay, we only know probabilistically what we'll get. And so because quantum mechanics can't predict which measurement results happen at a given time, only their probabilities, that's part of why it may not be complete. Another example is that quantum mechanics allows entangled states. Okay, so here the first position will be the particle 1 and the second position will be particle 2. And so you see this term tells us that particle A is spin up, particle B is spin down, and the second term is particle A down and particle B up. But because it is this a linear combination of them, okay, this is existing at the same time. So what this is, we call this the singlet state. It's a non-factorizable superposition, okay? And we say it's non-factorizable because notice that particle A is in different states in each term. So there's no common state that I can pull out. If they were both up, I could pull out up. from this parentheses here, but I can't pull it out because they're not the same. And the same for particle B. So this is simultaneous reality of conflicting states, of opposite states for each particle. So this is really what entanglement is. And that minus sign also is part of the richness of quantum mechanics. We can also have an imaginary number between here, not just a sum. Okay, so there's something even more rich that we haven't even spoken about yet. So basically, measurement of one particle here is going to collapse the whole state. So if I measure just particle A, it will collapse to one of these two terms, and the other particle will come along for the ride. So if I measure A and it ends up being up, I know that the particle B is going to have to be down, okay? And this is true regardless of the distance between them, okay? Even if they're farther apart, then light would have the time to travel during the experiment, okay? And so it's kind of like the particles know to be opposite. And this conflicts with Einstein's special relativity, or at least it seems to, right? It appears to. It's like they somehow just know, even though they're random, like even though we can't predict ahead of time what's going to happen. So the idea is that perhaps there are hidden variables, which we'll call HVs, that we don't see for some reason, and quantum mechanics is our statistical impression of them. Okay, so this is sort of the overall idea that EPR put forth. Maybe not, they didn't use the word hidden variables, but that's what people have come to call it over time. So in 1964, J.S. Bell came along and decided to put hidden variables to the test, specifically local hidden variables, and I'll explain what that means as we go. So the example he focused on was having two particles, A and B, starting out in this maximally entangled state, and they're created locally in that state, and then they fly apart, and they head towards two detectors, and part of those detectors are these polarizers, and we represent the state of the polarizer by some arrow, an A vector and a B vector for the detector A and detector B. He then postulated that there should be measurement functions, and what do? They give us the value of each measurement based on the value of this lambda, okay? And lambda is the hidden variable. It determines which value plus or minus 1 happens for each. Now the reason it's only plus or minus 1 is because spin is quantized in quantum mechanics, okay? And also by experiment, we find that it's only either up or down, regardless of the direction that we orient our detector. So it has to be able to reproduce that particular behavior. And also, this is the information that quantum mechanics is missing, right? Quantum mechanics can't tell us what the measurements are going to be. So if hidden variables have any meaning at all, they should be able to do that. And local, because each particle's results depend only on its own detector arrow A or B. It would be really weird if this measurement function depended on the orientation of this detector over here, because maybe this is like a light year away and the information wouldn't have time to travel before the end of the experiment. So somehow this thing has to be able to determine the measurement without relying on something so far away. And that's, again, to respect Einstein's special relativity. And if, it's the whole idea is to have a classical theory underneath of quantum mechanics, it shouldn't do anything strange like, rely on faster than light communication between the particles. So then, because we're talking about correlations, right, that's really what entanglement is, Bell said, well, let's look at the product of these two measurement functions to get the product average of them. So by classical probability theory, we know that the average value of a variable x is computed by plugging it into this integral, okay? And if you don't know what that is, don't worry. But this is a probability density function which sort of gives a character of how different averages play out for things that we can observe. Okay, so if we want to know the average of some observable thing like x, you plug it in here, you do this thing which is like a sum up over different weights, and it will spit out the average value of x for this system. Okay, so the average of the product of the measurements is putting the product of the measurement functions into this integral, and it weights them by the probability density, and you add them all up, and it gives you the average value of the product, okay? And this is what Bell called this PAB. And this still respects locality because, again, the measurement functions only depend on their own vectors, and the probability density function doesn't depend on the two vectors in a strange non-local way. It actually could depend on them as long as it wasn't depending on like the relative angle between them, right? So this also has to respect locality for locality to be obeyed. Now, why did he do this? He's doing this so that he can set up some kind of test to determine a requirement for local hidden variables. And this brings us to the derivation of Bell's inequality. So by the anti-correlation of this singlet state, Bell noticed that when the detectors point in the same direction, so their vectors are the same, A equals B, they have to give opposite results. Okay, so notice when A equals B, that A vector in the A measurement function is B. Okay, so then it's allowed in that case when they're parallel. In that case, B must be the opposite of whatever A is because one's up and one's down, right? Regardless of which outcome happens here. So for instance, if A is -1 representing down, then minus 1 is +1. So B is going to give us a +1. Okay, so this is the anti-correlation requirement. So from this and the product average that we just derived, he was able to derive the Bell inequality, and here it is. And he said that this is a condition that any local hidden variable theory must obey. So quantum mechanics and experimental data actually tell us what the average value of the product of the spins is for this system, and it's minus the cosine of the relative angle between the detectors, okay? And I'm going to use C instead of cosine, and I'm going to use theta A comma B just to simplify this relative angle here in what I do, in what follows here. So now, if we take these average value functions that Bell gave us and say, suppose they can achieve this quantum mechanical result, okay? Suppose that's possible. Suppose that local hidden variable theories can actually do that. He found that when we do that, we can actually get false statements or violations of his inequality. So to see how this is possible, let's take 3 different detector orientations, okay, 0, 90 degrees, and 45 degrees. And from that, we'll use this quantum mechanical value to actually compute different values that this product average should give us. Okay, and if we plug those into his inequality, we can get false statements like 0.707 is less than 0.293. That's just obviously not true. And his interpretation of this is that since his inequality is a requirement of local hidden variable theories, and putting quantum mechanics results into it causes a false statement, then local hidden variable theories are not compatible with quantum mechanics. Okay, the implication of this is that quantum mechanics, because it agrees with experimental results, then local hidden variables aren't compatible with physical results either. Okay, now this is going to get the experimentalists involved. Okay, so obviously anytime we have a theory, we have to then test it. Okay, so this spawned a whole host of experimental investigations into whether what Bell was saying was true or not. And overwhelmingly, people verified what Bell was saying. They were able to find these violations of Bell's inequality. They were able to test loopholes to make sure that they weren't overlooking certain things. And everything seemed to be going in Bell's way. He thought he had really disproven local hidden variable theories at this point. And this even continued after he died. A lot of experiments kept going, especially with the loophole tests, which we'll talk about later. But for the remainder of this talk, we're actually going to show that what people thought they were testing in their experiments may not have been what they thought. It might have been very different. So this brings us to our next discovery. So here we have a local hidden variable model disproving Bell's theory. Okay, so I'm going to take you through every step that I used to derive this thing. So first, I'm going to give you an overall picture. So we're going to start with this locally real hidden variable model. So we start with Bell's example, and we're going to assume no quantization, okay? Because the idea is if we want this thing to be classical, let's let it be fully classical. I'll add in quantization later, but it's actually much easier to see it without it, okay? So we start with both particles together at some point, and they have like a reference arrow on them, okay? Like a reference vector, A and B, that point in opposite directions, and that represents their anti-correlation. Okay, so they're sort of spinning together at first, but their reference direction are opposite by 180 degrees. Okay, and then they fly apart, but they're still rotating in the same way. Okay, so they're always pointing in the opposite direction as they're flying apart. Okay, and that's sort of a classical motivation of their correlation. And then we just basically draw out a very simple diagram for each particle relative to its detector and label our angles very carefully. Okay, so for particle A, its detector vector A here has theta A from some reference point. Okay, we'll just let this be the x-axis. And then we'll say that the reference angle on the particle, which I've represented as a cylinder just to make things simple here. The reference angle is phi sub A, and that's a function of time. So it's just spinning, okay? And over time, it's going to have some value, and we can know what that is. I'll show you what that is in a minute. And we're going to let alpha be the relative angle between that reference angle in the particle and the detector, okay? And because we're talking about classical thing here, we can actually have a reference angle here, right? It's not unreasonable to think that we could have some identifiable geography to a particle. And if we're talking about a classical particle, and that's what we're doing for a hidden variable theory here. We're letting it be fully classical. Similarly for B here, okay, we've got detector angle theta B, and then we've got the particle's reference angle, or the reference vector for the particle, and it is phi sub B relative to the universal reference there. And then beta is the relative angle between that particle's reference angle or reference vector and its detector. Okay, so this is relative, but it's relative locally over here, just like this alpha is relative locally over here. Okay, so we're not talking about relative between the particles at all. Okay, so notice alpha is still just a function of its own local detector vector right there. Okay, and that comes through in this theta sub A, which is determined by vector A. Okay, similarly for beta, and notice that beta's got the pi phase shift because it's 180 degrees away from A. Okay, and there's the angular frequency right there, and big T is the period. So then we're going to define locally real measurement functions very, very simply. We'll just say it's amplitude root 2, which is just to help the math work out, not very important. You can think of it as units or renormalization, whatever you like, and it's cosine of the relative angle there, okay? And this relative angle is the angle between the particle and the detector, not between the two different particles, okay? So it's still very local, purely local, and this little c means classical, right? Because I'm allowing it to have every continuous value here. It's not quantized yet. Okay, so we still have maintained locality, and notice I'm using t as the hidden variable. Okay, I'm just letting that be the hidden variable. I could let this whole angle be the hidden variable, but I'm going to let t do the job here. Okay, now our job to test this is to take the time average of the product of these things. So if I take the product of these two classical measurement functions and time average them, it actually gives us exactly the quantum mechanical result, negative cosine of the relative angle, even though relative angle is not involved here. Okay, so it actually gives us the relative angle involved there. And you can actually see this from this test. So the way I did this test was I made random times between 0 and big T, plugged that into these measurement functions, and then multiplied them together, and then did it again and again and again and again, and added them up and took the average. And then the average over all of the trials will give us this little red dot, right, for each one of these relative angles. So if I do that over all relative angles for a number of different settings, okay, what I found was the dots are approximating this negative cosine of the relative angle between the detectors. Okay, so the quantum theoretical curve in blue is approximated very nicely by this local hidden variable simulated data. And of course, as I do more and more trials, these dots hug this curve better and better. In fact, I had to keep the number of trials down enough so that you could actually see that I was using random numbers. It was actually very, very good agreement. And as you go to infinity trials, it's perfect agreement. And so this is confirmation, okay? Locally real hidden variable model is actually equaling the quantum mechanical result, okay? And this is something that Bell said was mathematically impossible. Now you may say, okay, well, Bell took into account quantization, and I haven't done that here. But I will show you that actually this does allow quantization, okay? But I'm just starting from a truly classical model to begin with. So first of all, this is possible. And it also obeys Bell's anti-correlation requirement. Remember this from the last slide. Notice these are very similar functions. Well, it turns out that we can pull this pi out of the cosine, get a -1, and what's left over looks exactly like the function a, but with theta b instead of theta a there. And because that's determined by the vector b, or in vector a, it's the a function with a minus in front with b inside there. And so then we get the b measurement function is negative a measurement function with b as its argument, okay, which is exactly this statement. And again, that c means classical because I'm allowing a full continuous value here. Okay, so you probably don't believe me here, right? You didn't get to see the actual programming of it or anything, but I'm going to now take you through the derivation of this so that you actually trust this result. Then we'll talk about how to add quantization in. So now I'm going to show you the proof that our locally real hidden variable model gives the quantum mechanical result. Okay, so we start with the product of the measurement functions, which I defined based on my diagram. First, I'm going to simplify them. And then notice that I kind of have a difference of two things. Like I've got this omega t plus phi naught, and then it's minus theta sub a. So that's a difference of angles. So I'm going to use the difference of angles cosine formula there. Okay, and I'll do it for both of them. And what that did is it got the detector angles into their own functions. Okay, that's kind of an important part of this. And then I'm going to take the pi that appears here and pull it out as a minus sign, which you can do for both cosine and sine. And then you can pull that minus sign all the way out in front. And I'm just going to distribute or expand both of these terms together. Okay, so I'll take this thing and distribute it into both of these and then distribute that into both of those. So I get 4 terms overall. Now notice in these middle two terms, there's a sine and a cosine, okay, of the omega t plus phi naught. Okay, so all those are the same. So I can pull those out, and what I'll be left with here is this you can recognize as the sine of the sum of those angles, and this thing here is 1/2 the sine of double this angle. Okay, so we got 1/2 sine of the double that argument, and then this thing becomes sine of the sum of those two angles there. Okay, so now we've got some interesting things here. Notice we've got a square of a time harmonic function and a square of a time harmonic function, and we've got a sine of 2 times a time harmonic function. Okay, so that should remind you of some tricks that we can do in a time average. Okay, so then we're going to note that a true time average approximates to an average over a period of big T when the time window tau is much bigger than that period T. Okay, this isn't actually necessary for this derivation. It just makes it easier. If you would like, you can skip this step and do it with a real time average and just make sure that it's much bigger than the period T. You will get sinc functions in that when you time average those harmonic functions, but you will find that because this when the time window is much greater than the period, you'll find that the sinc function dies to 0, and that's where this rule becomes true, okay? And if we're talking about things happening on like the Planck time, then this is very easy to achieve this, okay? We might as well use this approximation because it'll pretty much look like an exact equality at that point. So when you do this, okay, the time average over the squares, okay, is going to give you 1/2, okay? So you'll get the 1/2 for that, and for the double of the non-squared harmonic function, that's going to give you a 0, okay? And again, you get the 1/2 over here. What that does is it gets rid of this middle term, okay? It washes it out. And these 1/2 then factor out, cancel with that 2. And what's left here is you'll recognize this as the cosine of the difference of the angles there, okay? And that minus sign out in front, that's the result that we want, okay? So we get the minus cosine of the relative angle between the detectors, okay? So this is the way to achieve that quantum mechanical value from our locally real hidden variable model. So this brings us now to the quantized local hidden variable theory agreeing with quantum mechanics. So I just showed you the continuous variable one. Now I'm going to show you how we can actually achieve the quantization that we need. So quantized results can also work in a local hidden variable model. So we suppose that the polarizer has 2 types of transmission happening in it. Okay, so type 1 is the particle transmitted with the same phase with probability p tau 1. Okay, so the particle there, if this had, the phase would be like whatever these waves are doing relative to some reference point, okay? And so when they come in, there would be either like a 2 pi shift or a multiple of that or no shift at all, right? So that would be same phase. And then type 2 is if the particle's transmitted with a random phase shift, some phi tilde, okay, with probability p tau 2. Okay, so notice here the wave's slightly shifted from what it is. So if we just pick some reference point for the first case, then that same reference point would be shifted by some amount, some phi tilde, okay? So this is what we mean by this random phase shift, okay? So then we have quantized local measurement functions, okay? This CPQ means conditionally probabilistic, okay? And you'll see why here. So this A sub tau 1, A sub tau 2 here, these are quantized measurement functions that are only going to give plus or minus 1. This A magnitude here is just the scale value, right? So it's that root 2. And then the probabilities of each one of these types happening are there, okay? So this is the probabilistic measurement function, but it's only going to give you a plus or minus 1, okay? So in this case, the way we get these is we use the classical continuous function that I gave before, but we're going to take the 2-valued sign of it. So if this is 0, it's going to give you a plus 1. This will never give you a 0, and that 2-valued sign guarantees it's either plus or minus 1 for each one, okay? And each one has its associated probability, which is only between 0 and 1, okay? And it's got the other type, type 1 and type 2, are both going to add up to 1, okay? So it's 1 minus the first one for that type 2. And notice that these do not depend on the random phase shift because these are determined by the input characteristics, and then the random phase shift happens as part of the output, right? That's going to be what determines that type 2. Okay, so that's that type 2 sign is determined in part by the random phase shift that happens. And this is a classical thing. So this probability is a classical thing. We're saying that there is some mechanism within the polarizer that is happening, and we just don't know what it is. So this is a very classical probability. And so the question is then, does this model fully agree with quantum mechanics? And the answer is yup. Okay, it totally does. So when we do the same test now with these quantized measurement functions in this conditional probabilistic sum, we actually, again, get very good agreement. Although we have to take more samples to do it, it still works. Okay, and I even tested the lone averages. So I took the average of each one alone, and quantum mechanically and physically, that should be 0 for the lone one. And that's what we got. So everything's working like you think it should, but now we have plus or minus 1 being the only things allowed for the outcome here. So this allows us to have both quantization and locality in one theory, and it agrees with quantum mechanics for a local hidden variable theory. Okay, so this was a major triumph. Okay, and this is not necessarily the only way it would have to happen. This is merely showing that it is possible some way at all. Okay, and these two examples are enough to disprove Bell's idea. So at this point, people might be wondering, well, what about the Bell inequalities? It turns out that we can actually derive new Bell-type inequalities for truly local hidden variables using the models that we've just come up with. So now that we've found these local hidden variable models that agree with quantum mechanics, we can use them to derive new Bell inequalities that are actual requirements for local hidden variable theories. Redoing Bell's derivation using the locally real hidden variable model gives this inequality right here. So this is the same part as the left side of Bell's inequality. And we get this new function, this m function on the right. And it's given by this integral here. It's kind of a mess, but I got it from actually following Bell's derivation as closely as possible, but I used my measurement functions from the locally real hidden variable model. And so when I plugged those in and stayed as true as I could to Bell's derivation, this was the cleanest that the right side would let me get. Okay? And if I plot these things, if I plot the left side and the right side for various values of the relative detector angles, okay, I will see that I get a surface on the top here is the right side. This what this m function is. When I plot it out, it looks like this warm color surface, and then the left side looks like this cooler color surface down here. And you'll notice that it doesn't pierce up through this m surface. Okay, so this inequality is always true. This left side is always less than or equal to the right side. Okay, and this means that this thing will never exceed the right side, so there can be no Bell violations when you use this locally real hidden variable model. Okay, there can be no Bell violations. But this means that we had to properly derive the inequality, right? We had to start from a valid locally real model first, okay? And I'm going to show you later that Bell's problem really comes from that. He really didn't have a valid local hidden variable theory. So since our local hidden variable model agrees with quantum mechanics exactly, we actually don't even need to derive an inequality. We didn't have to go through all of this. So we can actually get an equality. Okay, and that's because the product average actually equaled negative cosine of the relative angle. So because of that, we get an equality from this thing. Okay, and it gives us this formula here. And this will also always be satisfied. So, and it turns out that the quantized local hidden variable model also leads to the same equality here at the end. Okay, so it isn't just the locally real hidden variable model, also the quantized model does this. And this also applies to more general Bell type results like the CH-SH inequality. And I also disproved that in my paper, but I'm not going to go into that in this talk. But that's because that inequality was derived from Bell's inequality. So all of the problems with Bell's inequality are inherited by this one. So why did Bell's model fail? Okay. The main reason, and there are a couple of reasons here, the main reason is that his mean value function for the product of the spins didn't have general enough dependencies, okay? And what happened is that this made his inequality too tight, and it caused false violations. So it didn't allow local realism, first of all, because his measurement functions were restricted to plus or minus 1. Now that is reasonable, right? That's what reality is doing, so that's a very reasonable thing to require. But we'll see that this is actually an important thing to consider at first, and then it can be relaxed when he just didn't even consider it to be possible. So if he had done that, it would loosen his inequality and prevent violations. And he also didn't consider quantization via loss of information. Okay, and that's how we were able to do it, right? We started with a locally real thing, and then we said, well, what if we just didn't have access to it? And maybe that's why we're seeing some quantization there. That would loosen the inequality by allowing local realism, okay? So that's the main reason, but it's actually harder to understand. There's actually an easier to understand reason why his model failed. So the additional reasons here, this I think is easier to understand. His model didn't include implicit facts that the lone spin components average to zero, which we already mentioned. So if you take the average of one of the spin functions over all the measurements, all the detector angles, it should give you zero. Okay, or I'm sorry, even just holding this constant at any given detector angle, it will give you zero, okay? This is quantum mechanical and it's experimentally verified, okay? And this is true for his model, right? His model is a two-particle system, and it's true, it's part of what should happen. And he did not include it in his model. If he had included it, he would see that his model was effectively non-local, okay? So including these actually implies discrete probabilities. And I show how to derive these in my paper. And you can basically reshuffle his mean value equation and these things around, and what you will find is you get these four probabilities, which are functions of the relative detector angle. And these are non-local probabilities. And remember I said that part of locality was that the probability density function had to also respect locality. And here we have probabilities that are non-local, and that's not good, okay? So what that means is that if he'd have noticed this, well, first of all, he would have still thought his local hidden variables were impossible because these are non-local probabilities. So he would have still thought he was right. But in that case, he wouldn't have bothered deriving his inequality. He would have just focused on those probabilities and said, hey, they're non-local, so we have a contradiction. Okay, and what our new results show in this paper is that local hidden variable theories plus some ignorance will create effectively non-local hidden variable theories, okay? And I showed this by starting with our local hidden variable model, then ignoring some parts of it to get this same model here that's effectively non-local, okay? So it's just our loss of information makes it appear non-local, even though it's fundamentally local when you look at the actual model. Okay, so this non-locality is just an illusion due to loss of information. Now, at this point, people are going to say, what about experimental violations of Bell's inequality, right? So, I mean, if we're showing what Bell said should happen is actually happening, doesn't that supersede all of this? And the answer is no. Okay, all of that same data, when you put it into our new inequalities, okay, so imagine here's a list of some data, +1, -1 for each of the measurement functions. If you put it into our new inequalities, just like this one, it's actually going to agree with it. It's actually going to show us that there is no violation. Okay, and you could use the equality we found that's even, a tighter version, and we'll find that that gets respected as well within experimental error. And since our local hidden variable models agree with quantum mechanics, which also agrees with experiments, we're guaranteed that this is going to work. Okay, this is definitely going to work. That's why we know this. So this is going to support our results. So every experiment that found a violation of Bell's inequality, that same data is going to find no violation with our inequalities. Okay, guaranteed, because our models agree with quantum mechanics, and quantum mechanics is agreeing with experimental results. Now, Bell's inequality, as we showed, represents an effectively non-local hidden variable model. Okay, so his original inequality is not actually a requirement of local hidden variable models. So local hidden variable models do not imply Bell's inequality. true local hidden variable models. He was wrong to call his model local hidden variable model because he did not realize it was effectively non-local. So when people put their perfectly good data into his inequality, they weren't proving anything about local hidden variable theories. Okay? Those violations were just good data put into a bad inequality. But our corrected Bell inequalities up here, okay, were derived from a verified working local hidden variable model, okay? So no data can violate them unless it also violates quantum mechanics. Okay, but because we've shown that local hidden variable theories actually do agree with quantum mechanics, we know that it's always going to agree. We will get no violations. But the question is, did we just get lucky with a special case? Like maybe Bell's example is just, a fluke? Nope. So the reason we know that it isn't just a fluke is that I was able to find valid local hidden variable models for all discrete quantum systems, not just 2 qubits, not just that one example. So the first thing I did was show how to generalize it to all 2 qubit states and observables, not just the example that Bell gave. So I proved it symbolically for all cases, and then I also did 10 to the 4th numerical tests to very high precision. Okay, we're talking like 15 decimal places or something. So an example for an arbitrary entangled mixed state. So it's true that there's something called the block vector for every state, and the block vector is a collection of mean values of observables, and it can always be done for product of observables, okay? So what I did is I created measurement functions for the principal directions that correspond to those observables, right? You could think of it as directions of their local detectors. So I came up with my measurement functions for each particle, and then I took mean values of the products of those measurement functions, and each one was truly local. It only depended on the local detector angle of that particle, okay? And the mean values of those products all match exactly the block vector components for the quantum computation, okay? So what you have here is the blue and the red bars are all matching exactly, showing that the block vector is exactly achieved by truly local measurement functions, okay? And what that means is that any product observable, any arbitrary observable for arbitrary detector directions can be constructed. So down here in the inset, you see that we have very good agreement right here, right? Notice like the 15 or 16 decimal places, at least there, we have exact agreement, and the local hidden variable theory is truly local, okay? And this is for arbitrary detector vectors for each of those particles. And this is not for the same state. This is not the singlet state. This is an entangled mixed state that isn't the singlet state, and it's for arbitrary observable that you get this agreement, okay? And I tested this for 10 to the 4th different arbitrary product observables there. So this is excellent indication that this was not just a fluke of Bell's example, right? It works for all 2 qubit scenarios. And block vectors, now because the block vectors agree perfectly, that means that arbitrary observables agree. And that's what I've shown right here. If you want to see what the measurement functions look like, okay, these are the measurement functions I constructed. So the warm colors are for particle 1 and the cool colors are for particle 2. And obviously this looks like a big mess. I just wanted you to see what it looks like as a function of the hidden variable so that you can see it always has a definite deterministic value at all values of that hidden variable. Okay, and then there's some mapping function that determines the quantization, right, which I go into in the paper, but I don't really need to show you that here. So this is all based on the local hidden variable measurement functions. Then I generalize this. This was just for 2 qubits. Then I generalized it to any many-body discrete quantum system, okay? And I solved it for all cases symbolically, and then I just did some tests for a couple systems, a few systems that my computer could handle in a reasonable time. Okay, so there's 2 qubits, and what this shows us is, okay, these are quantum observables. I take a product of quantum observables, one for each particle up to n particles, and Then I've got a product of local hidden variable measurement functions, right? Truly local, and they're sort of corresponding to these quantum observables here. And if this little red dot, which is for the local hidden variable theory, matches the blue dot, that means that I have predicted the quantum value using a local hidden variable theory. Okay, and you'll notice that the red dots are always right in the middle of that blue dot. Okay, that's the same as this example right here showing that arbitrary matching, or the matching for the arbitrary observable. So what you see here, there's two qubits. There's a qubit and a q-trit. Okay, again, all perfect agreement. A qubit and a q-quart. Okay, like a 2-level and a 4-level. Here's 3 qubits. And there's two q-trits, a 3-level and a 3-level, and then 2 by 2 by 3, and then 2 by 2 by 2 by 2. So that's 4 qubits there. For these last two, my computer was running out of numbers. There was a little bit too much memory to handle all of the measurement functions complexity. Okay, they get very complex, very complicated. So for these, I relied on the derivations to guide these results. For these are actual full numerical tests here. Okay, so these you might not trust these if you like, but they are supported by the derivations. Okay, and you can see that in the paper, and you can see it here with the numerical confirmation of the derivation-based stuff here. So all of this was really good confirmation that I can, in fact, do local hidden variable theories for general multipartite systems. So what about the loophole tests and pilot wave theory? Okay, after everything we've done, we have to talk about these too, just a little bit. So what are loopholes? Loopholes are experimental tests to see if physical reality itself might be acting locally real after all, despite Bell's violations being confirmed, with experiments. So this involves things like increasing sample numbers, that's one way. Separating detectors too far for light speed communication between them. So just to draw you a little picture of this, you've got 2 detectors. Then imagine the particle, just as it's being detected, sends out a signal to try to tell the other particle, hey, do the opposite of what I'm doing. Okay, and if we separate them so far that light speed signal would not have gotten to the other one by the end of the experiment. So like the experiment's over when it's only like halfway across there, that would be a way to circumvent any kind of signaling, right? So maybe something would break down and we'd see a different result in that case. Okay, so that's one example of a loophole test. There's a lot of other loophole tests, but this is just the idea. The whole idea is to catch reality doing something that we don't think it should be doing, right? Or something that we don't expect it to do. But we've shown that local hidden variable theories are compatible with quantum mechanics. We've shown it theoretically, we've shown it by example. And just one example is sufficient to disprove Bell's claim. Okay, so as far as Bell's claims are concerned, we're done. It doesn't matter what the loophole tests do or don't do. So loophole tests can't disprove our result. Okay, our result is already guaranteed true. Furthermore, we showed that local hidden variables agreeing with quantum mechanics are not unique. So if someone comes along and says, oh, well, your measurement functions didn't predict exactly what the measurement results are at each time, that's okay, because I found an infinite number of variations that also agree with quantum mechanics. So if one of them doesn't work, that's all right. It doesn't rule out the other ones. And there's another little caveat. If the measurement functions change very fast, like on the order of the Planck time, loophole tests probably can never detect them because we technologically cannot see down to that resolution and probably will never be able to. I don't want to say never, maybe it's possible, but it's going to be extremely challenging and we probably will never be able to actually test that. So loopholes are never going to contradict these results. Okay, all it could do is confirm our results basically. Pilot wave theory is based on Schrodinger's equation of quantum mechanics, okay? And it actually is an inherently non-local hidden variable theory, okay? So it's a different type of hidden variable theory. Ours is local, okay? So pilot wave theory really poses no threat to our results. It's just a different beast. So in conclusion, we've shown that local hidden variable theories are compatible with quantum mechanics after all. We've seen a lot of really convincing demonstrations of that at this point. So Bell was wrong, and EPR's idea was valid, at least in principle. Yet our world may actually still be quantum. Okay, we haven't actually proven that the universe itself is run by hidden variables. Okay, we've merely shown that they are compatible with it. But that doesn't change our results. Okay, we've still shown that local hidden variables are compatible with quantum mechanics. Otherwise, all these examples wouldn't work. And as a side note here, okay, the numerical tests are not the proofs themselves, right? The proofs are the proofs. But when we do a proof, we always have to check to see that there isn't some sort of glaring error. And that's really the benefit of doing numerical examples. And it also gives us a nice visual way to conceptualize our proof. And local hidden variable theories may merely be mathematically compatible with quantum mechanics, right? So, for instance, if our world is truly quantum, then this could just be a mathematical isomorphism, okay? And in that case, the extra predictive power of local hidden variable theories would be just like a mathematical artifact, all right? So that's a possibility too here. Local hidden variable theories are not unique. I mentioned this before. An infinite number of them agree with any system, and I found this especially working with my multipartite models. There are just so many ways to do even just one, and they all agreed with the classical, or they all agreed with the quantum results. So there isn't just one way to do them. Now, regardless of whether our universe runs on local hidden variables, we can still use these results, okay? So there's still a physical benefit to this, even if the world is truly quantum, all right? We can actually build classical systems that act like entangled states. That's what I've really shown here. So we could build hidden variable teleporters that act like quantum teleporters. We could build hidden variable computers that are capable of running quantum algorithms. And a kind of interesting side effect of this is that this could actually be viewed as a universal disproof of quantum advantage. So what's quantum advantage? The idea behind that says that there are certain things that quantum algorithms can do run by quantum systems that classical things cannot do. Classical algorithms and classical machines cannot do. And that's the quantum advantage. But what we've just shown is that there's nothing quantum that can't be done classically. So there is no such thing as quantum advantage anymore, except there's another caveat to that. This does not mean that quantum algorithms and quantum computers do not give us advantages, okay? And part of this is because of their compact size. So lots of quantum effects really start to become noticeable and usable when we're dealing with small things like atoms and particles and such. And that's going to be where the advantage really is still available, because that gives us high density. We can pack a lot of small things into a small space, and then get a great efficiency from it. From that point of view, okay? So there may still be advantages possible. And it may also be that it's very hard to build local hidden variable systems that mimic quantum systems, right? It may be very complicated. And I found that out when I was, modeling things like this 4-qubit example over here. There were a lot of complicated parts to that mathematically. Okay, it's not a very simple thing to do. So that may actually be some reason why there's still an effective quantum advantage, even though we've theoretically disproven it. Just interesting things to think about. So what are the challenges to this new discovery? The biggest obstacle is going to be people who don't read it but have gut reactions that it just can't be true. Okay. To them I say, don't reject what you didn't inspect. When new facts contradict our theories, we need to update our theories. Okay? And the proofs and examples that we've shown here are those new facts. According to Bell, what I've shown you is impossible. All right, and I've just shown you that it's possible. You can think back to special relativity. Okay, before Einstein, everybody implicitly agreed that time passed at the same rate in all reference frames. And if people had this "it can't be true" mindset, they wouldn't have even read Einstein's special relativity. They would have just said, oh, that has to be wrong. And they wouldn't have even looked at it, and they would have rejected it out of hand. So you cannot do good science when you do that, okay? Censorship, gatekeeping, these types of things that you will see, Archive does this a lot. None of that is scientific, and it really cannot continue if we want to do good science. In Bell's own words, what is proved by impossibility proofs is lack of imagination. And ironically, this applies to his own claim that local hidden variables are impossible for quantum systems in general. Okay, he came up with this impossibility proof for local hidden variables, and that quote of his came back to bite him just now. But we've shown that local hidden variable theories are compatible with quantum mechanics after all, and we can build classical devices that seem quantum. Okay, so Einstein ended up having the last laugh here. We can indeed get all the benefits of quantum entanglement without any need for spooky action at a distance. And I thank you for listening to this whole talk, and I want to leave you with one more quote by Einstein. Blind belief in authority is the greatest enemy of truth. Okay, you cannot learn something new if you simply believe something because it's written in a book. And it is possible for everyone to be wrong about something, just like they were about special relativity, until something comes along and changes everything. So you've got to keep an open mind. All right, thank you so much.